Welcome everyone. I'm going to give you a very introductory talk to give you an intuition of what large language models are and how they can help us solve real world problems. When we start the talk, I want people to ask themselves a question at the ending that what would you do with models or machines that can understand language? And to give a brief introduction, I work on the model serving team at Cohere. I've been there for around 8 or 9 months right now. Prior to that, I worked on an open source solution to productionize machine learning models at NVIDIA. All right, so what is a large language model? So a large language model is a machine learning model that can generate sentences and phrases very similar to what humans do. And what does generate over here mean? If that you were given a sentence, you would end up outputting what the next words were, kind of like a sentence completion or a phrase completion. It's trained on a large amount of data, and it can be terabytes and terabytes of tokens and words out in the internet and even private data sets. And then it can be used to generate these prompts, right? Given a question. A prompt over here is kind of like the input given to the model. So it's like, here is the sentence or the input in, and it generates a part after that, right? So that's what a large language model is. Now, it might sound like a bunch of mumbo jumbo, but what can it actually do? It can be trained to read, summarize, and translate text and even predict the future words in a sentence. So let's take a step back and look at the content over here. These are questions that actually asked one of the language models that we have at Cohere, and these are generated by it. Seems pretty realistic, right? It's almost entirely convinced that it's a human writing this. And then a question for everyone. Have you used a large language model? And it's a trick question because I think almost everyone has. An example of the use case would be Google search. If say you want to understand something about how Siri technologies work, you go ahead and bring out your phone, you start typing in, and before you even finish what you're looking for, you start getting these suggestions, both in the browser from the Google search itself and from your keyboard. So there's a race over here to understand what you're actually looking for. And then once you finally click one of them or hit enter, you get a result like this. This result kind of is a summary and right at the top of like what you're looking for. And it seems to be pretty accurate to the question itself, right? Even though I just searched Siri technology, it knew that it has to describe Siri technology to me. And then when you click on that, you end up going to the next page in there. And that page kind of has this highlighted section, right? Which was kind of what was summarized in the starting. So my question to everyone is, which of these steps do you think actually uses some form of language processing or the other? Step one, step two, or step three? Actual perception is that all three of these use language models in some form or the other. You have your keyboard, which has a very lightweight language model that is used to predict the next word. You have Google that's trying to predict it based on a bunch of other criteria. You have summarization of sort that gives you the output right at the top in a very concise summary. And when you click on it, it actually goes and selects the part relevant to it. But I'd argue there's another part over here that's kind of abstracted away and isn't very visible to us. It's a step called 1.5. It actually uses semantic search to give you the relevant results after looking through a large corpus of data. We talked about auto completion, we talked about semantic search, text summarization, and question answering. This is just 4 different tasks that a language model was used to do to actually get you a result. So you can understand how these technologies that we regularly interface with use language models in these complicated manners that we generally don't have a very good understanding about. Another really cool use case that I personally use a lot is when you're writing emails to someone and you get like a response recommendation at the bottom. It's kind of concise and short, but it's generally pretty useful for a short reply to people. And what happened, what got us to this point, right? So in 2013, there was a paper and blog articles and a bunch of really exciting news about this model called BERT, B-E-R-T. Why was it exciting? Well, it was the first time that Google found a way to train these language models at large amount of data, ended up giving pretty significant results. It was a huge leap in the understanding of what models can do previously and then what models can do right now. And then there was another leap which led to more recent trends, but we'll come to that in a bit. But why was this exciting? Why was this something that ended up being so groundbreaking? Well, for 20 years, Google engineers focused their talents on trying to optimize search and make it better and better. 20 years of effort was then almost entirely replaced by this one model that ended up just understanding language better than any deterministic programmable solution we had earlier. This was also then put into production within a year or so, which proved how easy it was to just bring machine learning models into production and actually solve realistic problems in production with them. So that was pretty fascinating. So we've talked about the different language processing and language based tasks that these models can do, but I'm here to argue that it doesn't just limit there, right? We have different modalities like vision, audio, robotics that can actually go and get improved by these language models. So when we're talking about language processing with vision, we have multiple interesting use cases. One of them very trending last year was the image generation case, where you had models like DALI, Midjourney, and Stable Diffusion actually generate pretty good images based on fairly simple prompts, right? So it took like that English, it got semantics of that and then built a visual understanding that it had to create these images. And this is very powerful technology. But before that, if you go back a few years even more, you would see that like these tools were being used in conjunction with others to do something like optical character recognition, image captioning, and visual question answering. Back in 2015, one thing that really made me excited about this area was that we had an image and we had machines generating very realistic captions for these images. I found that incredibly exciting because of two reasons. It proved that machines could gather, if not a very wide, but a very narrow understanding in specific domains if they're trained to do so, which meant that they could do at human level captioning of images that previously was something we didn't expect machines to be capable of. In this example, you'd see the caption being a group of people shopping in an outdoor market, and there are many vegetables in the fruit stand. Now, obviously, like there are nuances to this image that a model might not understand, but this caption itself seems to be pretty descriptive into what it's capable of. And the features it unlocks are things like if I go to Google Images and I try to search something, I can just search for vegetables and it will probably identify that, yes, this is something related to vegetables, and it will keep looking for things like that. So it's pretty fascinating what all these things can unlock. One really other fascinating part that ended up coming up was this model by DeepMind called Flamingo, which actually did visual question answering. So it wasn't just a one-time interface of like an image and then a caption, but a more interactive based dialogue, very similar to the interacting based dialogues we see with these language models now. An example, a picture over here shows the former president of the United States in what seems to be a very funny picture because people are laughing to it. But again, for a machine, why is this something that's important? Well, this image demonstrates a couple of things. For the first, you ask the model how many people are in this picture. And if you look back into the picture when I go larger, you'd see like it can be slightly confusing. So you see like 5 distinct people clearly, but as you can see, there are mirrors in the picture as well. But the model doesn't get confused by the mirror. It actually identifies there are at least 5 people in this picture, which is fairly true. What's the other part that's really curious is the fact that like it's able to guess where this picture was taken. Now, based on the picture itself, it basically guesses that it's a school environment, which isn't a bad guess, to be honest. It then asks how many mirrors are there, and then the model responds that there are at least 2 mirrors in this picture. What is the person standing on? And then it gets something wrong. And this is what makes things fascinating. It says that the person is standing on a rug, which isn't incorrect. But then you say that the person is standing on a scale. Now it understands the context of which person you're talking about in some way or the other. And the next question goes to what is he doing? What is he doing on the scale, etc. And he's looking at the scale, and then you ask the model, like, where is Obama's foot position? It says that it's on the right side of the scale. So you're kind of building intuition into the model to understand what's really going on. It's a very interactive experience, but you're getting the model to understand deeper and deeper with all these questions. And then you ask it what happens as a result. The model shows, or the scale shows a higher weight, which is good, right? It's able to reason about and build a good understanding of what's going on, but then it's also able to look deeper and deeper, and you have much more fine-grained control over the kind of depth it can take. And then the next question is the person aware of it? And that's fascinating, right? That's a very open-ended question, and it's not something machines generally are very good at, but it says that it thinks that he's not. Do you think that's why people are laughing? And that's how you've come to make this model understand, like there's very deep humor in this for a model to get to, and you ended up helping it get there. which to me is very fascinating. The ability for you to have this interactional experience where even if a model itself doesn't immediately say that, hey, this is a meme or a funny picture about XYZ, you can actually get it there. And this is why prompting a model in the right direction ends up being such a powerful tool. And by prompt engineering is a very exciting space to be in right now. And then coming back to prompts, given the prompt that you're giving, you could actually generate interesting images. This is just images of Kermit the Frog in different movies. You can see the textures and the styling of the movies captured in these images. If you look at the one for Kermit and the Frog in the Matrix, Kermit the Frog in the Matrix actually is fascinating to me because it keeps those glasses, which to me remind me a lot of the glasses that actually were worn by Morpheus, which is great. But it then puts it into different backgrounds and the color tone is all captured as well. To me, this is very fascinating. Not only does image generation hold potential, there are other use cases where language models in conjunction with these could be used to do something like image and painting and a bunch of other tools. Like you probably wouldn't ever have to use Photoshop in the future, which is fascinating to me. And then apart from these generative AI tools, what actually is like an immediately well-performing sector? Well, OCR and image captioning. As I mentioned, like image captioning before gives you these keywords or tags for these images that will actually be useful for you when you search in. So when you search Elixir, for example, it's actually able to identify both text that's actually in the image, but also context-based search. For example, it saw Elixir with coffee, so it kind of associates that with coffee. And the same goes with like different pictures and videos of cats or dogs, any other things. It's incredibly powerful in the sense of the fact that these machines are now able to get enough semantic to get to a point where they're able to build these solutions out there that save us minutes and minutes or hours of work. So I've talked about a bunch of different technologies that actually leverage language models, and I've put some of them up in the page over here. The most popular one recently, what I've heard of, is probably ChatGPT, which is a conversational AI-based model that actually is built on top of a language model. These are becoming more and more a part of our lives, and they show more and more utility based on the modality in which they're used. So I've talked about the different types of language processing, but I'm going to take a break here and point you to a channel that might detail both how transformers work, their inner workings, how old language models like BERT used to work, and so on. Jay is one of my colleagues at Cohere, and he's actually helped with a lot of these slides too. He has YouTube and Twitter as a really active form of media that he uses, where he talks about both AI ML in specific language models, but in general trends in the industry from like stable diffusion based image generation to the other more fascinating parts. And I recommend you to go look at that after this talk if you are more curious. I'm going to stop here and talk more about specifics of Cohere as a company, largely because I believe like it's one of the most powerful toolkits people can use to integrate NLP into their products without having a very, very strong understanding about NLP. So what's exciting about Cohere? For example, if you look at this paper itself, it was a paper published maybe like 3 or 4 years ago that talked about or introduced this new kind of architecture or layer called a transformer. A transformer is now a fundamental building block of most of our popular deep learning models out there, from vision based and other transformers that are used in stable diffusion to ChatGPT and so on. The author right there in the center that's highlighted, he's our CEO and co-founder, and he's been a part of both the groundbreaking parts that happened at Cohere, but everything that led up to it, and that makes me very excited. So how is NLP at Cohere? So if you look at a large language model, you need a lot of data and you need to parse it and get it into a usable format. You can use public data sets like Common Crawl or even private data sets that you yourself annotate or fetch. And then you can train these models, but they're very computationally expensive and they can take a large amount of time to train. If you do want to train these models in the billion parameter scale, then you'd ideally want to go down the approach of training them on TPUs or other accelerators and need high degrees of parallelism. So we use Ray in conjunction with JAX to train on a large set of TPUs and get our models to a really good quality of performance. And then when you get a model trained, the next step comes into taking this trained model and then evaluating it for different tasks. Once you evaluate it on different tasks, you get a good understanding of what the model looks like and if it does well on a bunch of like standardized data sets. There's another degree of evaluation where you look at this model and then you evaluate things like Does it perform well on specific tasks that you care about? Does it look at like different things? Is it introducing toxicity? Did you filter out the right data from the data set while training it, and so on? There's steps over here that are actually exciting and very open-ended into looking at like how biased the model is and so on, but I'm not going to go very deep into that. The part after that that actually excites me a lot is the part where I come in and my team comes in, the model serving part. Once you've got this model and you've made it into a state where it's servable, it then is a question of making sure that it's productionizable, in the sense of the fact that yes, you can host one model, but how do you scale to traffic? How do you optimize the model to be most performant? What kind of hardware do you use? What kind of configurations do you use? A lot of these times, these larger models, they don't fit on a single GPU. So you need to use multiple GPUs, and there are configuration challenges around that. Then there's cloud-based challenges into like the actual deployment of the model and interfacing with it, the ability for you to like get different functionalities into the model and so on. And then once that comes in, obviously you get like this last part, which is like this very neat SDK that abstracts away all the steps before that. You don't even have to worry about training your model. You don't have to worry about the cost of hosting the model. You just send a request and you get a response via the client SDK, which we have in Go, Python, JavaScript, and I'm guessing you also have a CLI for it. So as you can see, there are a bunch of steps and challenges that go into training these models and building something up that actually is productionizable. Cohere just abstracts that away to make sure people can focus on the actual solutions instead of focus on the training of these models themselves. So three of the really powerful use cases that we have out there right now from Cohere is the embed, classify, and generate. I'm going to talk a little more into all of these and kind of give you a context of what they are and the capabilities that they can bring. Representation. Now, representation is an interesting concept. It's a word that can be loosely used to talk about how the model learns to represent the data you give it in the form of these numerical numbers. Well, ASCII is a common representation people use and machines use to encode the text data. But as you can see, ASCII doesn't really do a good job of encoding context. As you can look at the image over here of the emoji, that's actually something that isn't really understandable from the perspective that like a model might understand it through Unicode, but not know the semantics or the meaning of it. So you need to go deeper. For many applications, just using the ASCII representation isn't really good enough. You can use it to check if a password meets the specific standards you want it to. But if you want to solve semantics, summarization, you want to build powerful classifiers, and you want to do translations, you're not going to get far. This is what language models bring, the capabilities that I've listed here, but then so much more, right? You can do whatever you want with this representation, apart from the semantic meaning, summarization, the classification, and translation. You could actually use this to even build in a little more powerful applications in the ending I'm going to talk more about. So like I said, an embedding is basically a vector of numbers, these floating point values that capture the semantics. And you can ask me how that happens. Well, as this model is trained, there's a intermediate representation. It then abstracts away. And this abstracted intermediate representation is something that is used to understand whether something is similar or not to the other. To simplify, you can have three different questions. How's it going? When do you open? And hi, how are you? Now, based on the semantics of these in the vector space would be closer or separate from each other. So as you can see, how you are is very similar in what it's asking you in the semantic meaning to how's it going. And that's why these two end up being very close in vector space to each other. These vectors are generally of large dimensionality, but I've reduced it to just three to show you how simple it is to just compare these. Think of it using something as simple as like cosine similarity or other interesting distance metrics to get whether two things are similar or not. Well, how is this useful? When you look at different texts coming in, you can actually cluster them together or even put them in space to visualize them, see how similar texts end up being in the same space. And as you can understand, if similar texts are in the same space, you can easily build classifiers or models that cluster and get interesting use cases out of that. One of the clusters over here is the one denoted by 1, 2, and 3 that has questions like what are the hours, when do you close, and are you open on weekends? And this talks about the schedule, right? The second part talks about like the pricing and the menu. And so that's into one cluster. And then the last one talks about like questions about delivery and takeout and so on. So it's pretty useful to see these, and a lot of these are actually out of the box, fairly good and usable for your problems to solve interesting use cases. So let's talk about the classification use case. There are effectively three ways to build classifiers using these language model embeddings. The first one comes from using the baseline embeddings, which is what we refer to as these embeddings that are already trained and available out there without being fine-tuned for a specific use case. You then give it text that it embeds and a class label, and you can train a classifier. You can even use something as simple as logistic regression and get fairly good performance. And obviously, more complex classifiers can likely yield better benefit. So you probably need tens to 100 of these examples to actually get you a fairly good classifier. And as you can see, like that's still annotatable by a person, right? You don't need to go around and hire an annotation team to actually get a good quality classifier. So, well, let's talk deeper about classification. Cohere offers classification and without a very strict sector of classification. So you can use it to do anything. And how do you do that? You use something called few shot classification, which I'll talk about in a bit. But as you can see, you can use classification in different contexts for language models. One of them is to understand the action that a system needs to take, the intent of a customer. So if a customer is asking you about like the delivery schedule or like where's my package or questions like that, you can direct it to a specific sector and engage that sector itself instead of just generically sending out the message. So you can see it being used in customer service centers and so on. The other really cool part is content moderation. Now, language models themselves are able to get a fairly good understanding of whether something is toxic or something is politically charged and so on. And you can end up training classifiers just purely on that and build really good toxicity detection. So you can use that on social media and other places to actually detect toxicity and probably take action on the folks that do that. So you have text classification. You can train your classifiers in one way. Let's talk about the other way. So for few shot classification, you can give it a couple of examples. And based on the couple of examples you give it, it trains a classifier on the fly for that use case. So you can use maybe 5 or 10 examples and you can still get away with that. Once it's built that classifier on top of these using the embeddings, you can then keep providing inputs and get a fairly good response. So imagine you never actually trained a classifier yourself. It was abstracted away. You provide examples in your request as long with the inputs, and it trains a classifier and makes a prediction altogether. And that's one of the other use cases for classification that Cohere supports. But let's talk about the third kind of classifier, the one that you probably want to go with if you want to build really powerful classifiers and your use case actually requires a very high quality. You could fine tune your classifier based on input text and then extract embeddings from that. So once you fine tune, what ends up happening is that this space in which these vectors are organized, it reorganizes based on the content that you fed it in. And when it reorganizes, it gives you higher quality vectors, right? There's a more clear distinction between the image A and the image B. And you can see like the stuff that is related to you to be classified ends up being in two separate spaces. Why is this good? Well, the better quality of embeddings you get, the better the classifier that you can train after that. So you can fine tune and build this classifier as well for things like sentiment analysis and so on, and Cohere supports that as well. Let's talk about semantic search. I mentioned this is step 1.5. If you go back to the initial discussion about Google search, and I want to talk about how powerful this is and the capabilities language models have unlocked with it. One example is you heard of PageRank, which is Google's algorithm for sorting out results for users. This is something similar where you re-rank results for users based on the contextual meaning those things hold. So if you're giving results to users, you can maybe gear that so that you re-rank them in the appropriate order of interest to a user or contextual similarity. Think of it as searching Netflix for a specific movie. You end up typing something in that search bar on top, and it uses some kind of semantic search to get you the results based on the order you need it to be. The other part that I find really fascinating is called dense retrieval. Again, this is also used in the search example that I gave, where you look at huge variety of documents or corpus that you have to search through. You embed embed the query that you have, and then you try to associate that with the documents. So you'll end up doing a similarity search across a huge vector space and look at different embeddings, and that will give you an understanding of like how related something is to the question you're searching. So think of it as a bunch of research papers, and you search for something like maybe Bloom or something similar. Now it will go through that, get the context of it, and find the paper that talks about Bloom semantically in the way that you phrased your question. So that's about the classification side, about the representation side. But now I'm going to talk about the generative part of these models, right? The thing that these models are actually trained for, and really they've been performing really well in. What is a generative model? A model that takes in input and then gives you output. And that's a huge and flexible paradigm, right? Think of it as a model that is able to output anything based on whatever you instruct it to. So you could definitely not give it a very strong instruction, just give it a sentence or a paragraph, and it can go on and generate the next. Maybe you want to use that for stuff like blog posts and so on, right? But you could also ask it to summarize, and you could also ask it to extract specific sections of your document by paraphrasing it. And that's how open-ended generating truly is. It's an ability for you to gear the model towards whatever use case you want with little or no effort. An example would be like just simple completion, right? But like, what is the prompt? What is the input going to the model, and how does that matter? Like I said, prompt engineering is becoming an increasingly important part, and I'll explain why. You have a section of text over here, and you follow that with a just two words, right? In summary, followed by a comma. And that's all that your prompt is. So as you can see, like it's pretty similar to like communicating with someone. They tell you something and you just say like, okay, can you summarize, right? And then the model is able to get fairly okay completion or a summary, and it works decently well for most tasks. But then you have to go into like another set of iterations and fine tuning and more exciting changes to actually get really good summarization out of these models. In some way, like this ability for language models and generative models to do a variety of tasks becomes more and more diverse and more powerful into what the capabilities are as the model size increases. But you can generate text, and generating text is always shooting in the dark. And why is that? Well, these models that generate text, you could make them generate deterministic text, but in most use cases you want to have some degree of flexibility or creativity to these models, right? So you can actually generate multiple generations from the model and pick the one that's most reliable. Now, what is a reliable generation, you can ask me? So say you have a bunch of outputs and you want to pick the best generation. You look at something called likelihood scores. Now, likelihood scores kind of encapsulate what the probability of this sentence or phrase or completion of occurring in the natural world would be. So it gives you an understanding of like, if something is more likely to occur out in the open, it's more likely to be something that you're looking for. And based on that assumption, you look at the likelihood scores and you sort out whatever you want. Now, in addition to that, you might be looking to do something similar, right? For example, paraphrasing or something like that. Now, if you're paraphrasing, you can't always look at something that's most likely. You need to be a little smarter in the sense of the fact that you look at these outputs. Remember, we talked about representation. So you're going to use that now. You embed them. And once you have this embedding, you can do a similarity search of your input to your candidate outputs. And you don't want something that's too similar, but you don't want something that's very far from what it's actually saying. So you kind of find a sweet spot, and there's a bit of like experimentation involved over there. But now you've amplified your ability to paraphrase by embedding these documents and looking for the right sweet spot inside of that. We've talked about how these models can generate, and they're very open-ended in the capabilities. But I want to take a step back and kind of talk to you about some of the common issues that can happen with these models and the general perception these models have. Why is it important to not confuse the ability of these models to sound intelligent with general intelligence? Well, I'm going to take you back to this movie called Hitchhiker's Guide to the Galaxy, which is based on this book. But it talks about, in the movie, it talks about how this machine was built for being a general form of intelligence. And then To that, you ask a question. What is the answer to the ultimate question of life, the universe, and everything? Now, as you can see, this question has a bunch of things wrong with it in the sense of the fact that it is open-ended. It's not something that you generally expect a machine to have an understanding of until it's like fairly good in how general it is as an intelligence. But if you give an input like this to a language model, it's probably going to generate something very similar to what that did, right? Which is you have it generate the answer is 42, which is exactly the same dialogue from the movie itself. So here is your takeaway. These models are good at remembering, at generating text that seems factual and true, but they don't actually have themselves grounded in a true source of truth. And why is that? If you don't provide this model context or information about something you're asking it about, it has what we call the ability to hallucinate, where it just makes up stuff. And that ability for it to make up can be very lethal if people misunderstand these capabilities of these models. So you want to exercise with caution, specifically if you're asking the language model questions that you generally ask Google without knowing if the model is actually basing any of its statements or results in actual truth. So I'm going to talk very briefly about grounded language models, and this could go on in a talk of its own. But I find this exciting specifically because of the capabilities that it unlocks and the ways it augments language models to actually give you useful information. Now, you would have heard Bing homepage has like an integration of ChatGPT, where it uses a language model to actually augment the search. So you can actually interact with it and ask questions to it, and that model tries to use and tries to ground itself in actual search results. So when you currently search Google, you'll get pages and pages of results for what you're looking for, but you don't always have time to do that. You'll be seeing targeted ads, you'll be seeing other content that's just ranked and might not necessarily be what you're looking for. So if I ask a question, for example, like in which year did the Civil War happen, a language model can just make that up or remember that based on text that is already read. But if you wanted to give you a deterministically correct answer, you want to augment that with some backing, like back it up with some knowledge, right? So you get search results based on the query the user has, or maybe you want to rephrase that question the user has into a different format based on context that you already have. So for example, if a user asks you, what is the Civil War? And the next question is, when did it happen? If you just copy paste when did it happen into Google search, it's not going to give you a valuable result. You want to incorporate context, or you want to bring in more details into your search to get the right results. So you augment that question, search Google, and you get a bunch of search results. Now, when you get these search results, you now have a question, the question of like, which of these search results is actually going to contain the answer I want, right? The content that I actually want to refer to. So you take that as input prompts and you give it to a generative model, and you get an output. But if you give all the data of all the search results, you're going to overwhelm the model and not get something useful. So why do you want to take another step and do something a little different? Well, instead of feeding in all the input data into the model and getting search results, you want to then embed the data, get the representation out of that, and get a similarity of the results with the content of these models themselves. And when you do that, you get prompts for the model that correspond to text that is semantically similar to the question. That can be then fed into a model. You can even summarize large amounts of text if that entire text talks about your answer, but it's not exactly what you want. And then you get the actual output to the user. So again, like there are different things going on over here, right? There's general generation that you use to reword a question with context. You use search results to actually augment your input. You then look at the search results and rank them, or like extract the parts that are actually useful to you based on semantic search. And after you do semantic search, you can actually go ahead and generate from those semantically similar results the actual output you're looking for. And this pipeline actually gives you a fairly accurate and factual response. And this retrieval augmented language models is an entire area of research. It's extremely fascinating. And using Cohere's API, we actually built something very similar to this. We have a GitHub repository up there that's called Grounded QA.
that actually does something very similar to this, and you could fork it, play around with it, and do a bunch of things. Feel free to scan that QR code to actually join our Discord community and refer to any of these docs and links to actually look more about what Cohere is, how to use the API, and so on.